Nice. I wonder if I'm gonna see. I'm just about to wait and see if he'll join. Let's see if he will join. It says recording in progress. Recording in progress. Admit. Uh, mhm. Hey,
Hey.
hey, you got a cool background.
Yeah, yeah. And I should probably try to turn off my background here, since I actually have a nice looking bookshelf.
Oh yeah, that's cool.
How- yeah, how are you doing?
Doing all right.
Yeah, sorry for this mix-up. It's I just uh, managed to get completely confused by time zones.
Hey man, I still don't know time zones either. I still Google them.
Yeah. That's of course how I do it too. Uh, yeah, at least sometimes zones I have a feeling for. Sweden versus Britain, that's the hardest because it's 1 hour apart and I can never remember which one is which.
Yeah.
I'm starting to understand California time really well because I'm involved with a project with some friends in California. So basically, I start the day by having a morning meeting as they're going to bed. And then in the evening, I have this meeting where I'm slowly getting more and more sleepy while they're getting very energetic with today's coffee.
Yeah. Yeah, we all need sleep, man.
Yeah, and sometimes you can make it work really nicely when you have a nice distribution across the time zones.
Yeah. Yeah. I'm glad you're doing all right. I'm doing all right. I get up early anyway, so it's no big deal to wait an hour.
Cool. Yeah. And you even got a ceiling fan. You're in a warm place. We
Yeah.
have a snowstorm out here.
Oh, I bet you have that heat blasting, huh?
Yeah. And it's funny because all my British friends were talking about yesterday they had horribly bad weather. This is their bad weather from yesterday. It kind of comes 1 day later here.
Yeah, it catches up. Yeah. So before I go
But
and asking more science questions, well,
yeah,
about like
please.
rockets, I wanted to go over what we went over last time was about antimatter and stuff, and what I learned about the conservation of quantum numbers. That you were right.
Yes.
If even if you could violate it, it would not destroy quantum information. And
Yeah.
apparently, it actually violating charge parity symmetry does happen, just not often enough to explain the matter antimatter imbalance.
Yeah, so there are some symmetries that nature seems to care about much more than others. So the most famous ones is of course charge parity symmetry, where if you look at a muon, for example, in a mirror and look at the decays, you will find that oh something is wrong. You actually need to flip time to make everything work. So you have a charge parity time symmetry that seems to be strict, but just charge and parity, nature fails at that, but only when the weak force is involved, which is kind of really awkward because most stuff you see around you doesn't involve the weak force. In fact, if you point at any phenomenon around you, it's most likely just going to be electromagnetism, a bit of gravity keeping stuff down. Finding something around us that you need the strong force to explain is kind of tough, which means that the weak force is kind of really wimpy, except that you need it for explaining why the isotopes are like they are. So in some sense, the kind of chemistry we got is because of a weak force, but it's a very subtle influence.
Yeah. Yeah, and I was also reading about the four forces and why we don't use, or excuse me, why we only use electromagnetism. Apparently, the strong force is too short ranged.
Yeah. And this is quite often explained by talking about the mass of the force carrier.
Yeah,
So in the case of electromagnetism, it's photons. They're massless. So they have essentially infinite range. Gravitons are probably massless too, they're a bit weirder, but again, infinite range, which means that even though gravity is really wimpy, after all of Earth's mass is required to pull back on this cup, and I can still resist it by using a little bit of electromagnetism in my muscles. But then the strong force, that's going to be in an atomic nucleus, it's going to be exchanges of pions, which is the residual part that you get outside the protons and neutrons. Inside you have the gluons. And again, they're fairly massive particles, so the range becomes super short. And of course, the vector bosons that you have a weak nuclear force, again, they have a rather hefty mass. So the range is going to be super short.
Yeah. So the gluons essentially decay over that very short, I think it's a femtometer or something range. Let's say
Yeah,
the strong force was long ranged. Would it just collapse everything into one big nucleus, like the electrons and stuff?
I wish I could give a good answer, honestly.
Oh,
The strong nuclear force is complicated. So if we were talking about gravity and just ask me, okay, Anders, what happens if you dial up the gravitational constant? It would be really easy to give an answer. Yeah, everything squeezes together and you get a lot of black hole. Electromagnetism, what if you made the charges more powerful? It would be a bit more subtle because you would have things like, okay, protons would attract electrons more strongly, electrons would repel each other. So you would probably get an effect on the size of atoms and molecules, which would probably do nothing good to the chemistry we're building. It's a bit more subtle, but it's probably relatively straightforward. You can actually calculate the sizes of planets based on the ratio between gravity and electromagnetism. And you could calculate how much bigger and smaller they would become. Now, the strong nuclear force, though, is tricky because you have three kinds of charges. You have the different colors, and conveniently we call them red, green, and blue. But it's kind of it's an orthonormal basis basically, uh, and making it stronger. Yeah, you would get more in strong interactions, so it probably would strongly change the stability of atomic nuclei. So the most obvious thing is presumably they would be able to hold together way better. You would get much heavier elements that way, which would probably produce a lot of very interesting effects of fusion. And fusion itself, of course, is to some extent making use of that the strong nuclear force can release a bit of extra energy when you get closer together. That's bingo. The problem is, of course, that it might also make some particles more or less stable. So neutrons, for example, right now they're mildly unstable. They decay using the weak force to protons. But if you have a stronger nuclear force, you might actually get dineutrons that would become stable. You could get neutronium much more. So my guess, without knowing anything or doing a calculation, would be that you would change the universe quite strongly. Pardon the pun, but yeah. But it is subtle, and it wouldn't surprise me that you could get these really weird effects because the color forces are not at all intuitive. That's why the physics of neutron star cores is just so weird.
yeah. Yeah. Plus, the temperature at the core is very high. Well, obviously, it's high everywhere, but it's very, very high at the core where it's theorized that neutrons and protons can melt down into quarks.
Yeah, so that is an interesting thing because the source of that temperature is partially pressure and partially the initial temperature of the start.
Yeah.
So when you have a garden variety supernova squeezing stuff together into a neutron star, at first it cools very fast through the Urca process. And Urca, it's kind of an interesting thing to see that quite often physicists spell it out with capital letters as if it was an abbreviation, but it's actually a name for a casino down in Rio de Janeiro. I think it's closed now. But basically, George Gamov and a friend of his, they were losing a lot of money at roulette there. And then we are talking about neutron stars, and they came up with this process, and they named it after a casino because they lose energy as quickly you lose money at the roulette table. And the basic mechanism is that you have these very excited protons and neutrons interacting, and they can release energy as neutrinos. And the neutrinos are happily going through most of the star and are escaping. Normally, neutrinos are really tricky to cool anything down with, simply because you need to make them using the weak nuclear force, and they just don't carry away that much heat. But in the first few seconds of a neutron star's life, it goes down from a billion degrees, mere millions of degrees through this process. Then it gets a bit more stable and it shuts off that neutrino production. Now it needs to cool in a normal way. And now it has a big problem because, well, it's not that big. The surface area is really tiny. So even if it's very hot, it can't radiate away that much. And also, of course, you get this heating by simply compression. You have essentially a solar mass of material pressing down on the core. So particles down there, they're forced to move very fast to resist that pressure. So there is a lot of fun physics that could happen there. It's still far below what's known as the Hagedorn temperature, where you expect actually quarks to become free. from protons and neutrons. But there might be forms of quark matter that are stable at these lower temperatures but higher pressure. So you would expect them to kind of melt together into this denser form, which is right now totally hypothetical. Everybody's kind of watching data from neutron stars, trying to figure out the equation of state. How does pressure and density vary with each other? Because from that, you can kind of rule out various theories. And this is very, very tricky astronomy work and very tricky modeling work. So I don't know how much I would trust anything of it, but it's just very active and cool research.
Yeah, it's cool. I think the hadron, I forget what you called it, temperature. I think it's something like 10 to the 30th Kelvin, it's right here. It's very high. And where quarks, where you get the quark gluon plasma is like 10 to the 12 Kelvin. So it's a huge difference.
Yeah. So you can of course cheat by just take two atoms, accelerating them to a very high energy and bang them together. This is of course what we're doing at the Brookhaven Heavy Ion Collider. And you can actually get up to temperatures locally there among those few protons and neutrons that are also getting high. So they're of course hoping to see some signatures of proper quark gluon plasmas. And to some degree, these plasmas are a really interesting environment because they're generating, of course, random new quark antipart pairs and new gluons. And since the strong nuclear force is very nonlinear, the gluons interact very happily with each other, which is not true for gravitons and photons. Light passing through other light normally doesn't interact at all. But a gluon beam, if you could get it, and another gluon beam, they would literally glue together and a lot of weird things would happen there.
Yeah. Yeah. It would be cool. Well, it will be semi cool to visit it. Not too close, obviously, because you'd get vaporized, but close, a few
Yeah.
billion miles away. Yeah.
Yeah, there is a lot of physics that you want to watch from a safe distance, and maybe interestingness is kind of proportional to that distance you want to be away from it. I mean, active galactic nuclei, whoa, that seems so impressive. But I noticed that you need a lot of heavy tungsten shielding if you want to be even within 1,000 astronomical units away. And quite often you get bursts of particles that might get through that too.
Yeah, I know it would kill you. Yeah.
Yeah.
I was gonna.
So you want to observe from a safe distance. The wonderful thing about space is, of course, that its three-dimensionality means that most forces and most particles, they get diluted with the square of the distance. This is incidentally why nuclear explosions in space are much less dangerous than nuclear explosions or in a planetary atmosphere. Because you don't get much of a pressure wave. Yeah, you get a lot of very nasty radiation going off towards infinity. But if you're sufficiently far away, you're just getting a nasty radiation dose. And add a few miles more, and you're relatively safe. On the other hand, on a planetary surface, you get a pressure wave, which is kind of bad. And it's, of course, even worse in a denser medium like an ocean, where you get a real shock wave.
Yeah. So, do physicists know the exact limit between neutron star and black hole? So, a neutron star will be about 10 to the 17th kilograms. I don't know where exactly the cutoff will be where it would turn into a black hole.
So that is the Oppenheimer-Tolman-Volkoff limit. So there is the well-known Chandrasekhar limit, well-known at least among astrophysicists, which is kind of the upper limit for what a star and how much mass a star can have before collapsing to become a neutron star. And then there is this upper limit on that's estimated for when a neutron star would start collapsing. Now, the problem with that one, as the numerous names attached to it hints, is that this is a complicated calculation. And I mentioned that we don't fully understand really, really dense matter that is interacting with the strong nuclear force. So it's somewhat tentative. So you could say, nah, we actually don't know. We have to do empirical observations. It could also be, of course, that there exists some super weird state of matter in between neutron stars and black holes. However, it's not a big space. So a typical neutron star is about 10 kilometers wide. It's a city-sized thing. A black hole with a solar mass is about 1 mile across. So you have a factor of 10 in between. And there is also something called the Buchdahl limit, which is a theoretical limit on If you have a static object of some kind of matter, we imagine whatever matter we can imagine, then the equations of general relativity suggest that if you go below a certain limit, the pressure at the core becomes infinite, which presumably means that, okay, now at least the core is going to become a little black hole just because the pressure itself has so much energy that it actually bends space. And that is a little bit larger than standard black holes. So the space of really weird matter that could make out something super dense doesn't seem to be that big. Of course, theoretical physicists will always come up with some crazy new thing that might fit in, but nobody actually believes there is any such state.
Yeah, it's cool. And I had a few more questions. I
Sure.
remember I sent you a tweet a while back about the Planck mass, and I told you, I said, why is that the lower limit of mass? And you said something along the lines of, you need to quantize gravity, and we physicists don't know, like, so what is that? Can you go into that?
Mm. So when you think about the units of mass and length and energy, etc., one classical question is, what would a natural unit be? Uh, I've been talking about miles and kilometers, and these are just arbitrary human-sized length. It makes sense to talk about a mile and a kilometer because that's a distance you can walk. When we talk about a meter or a yard, well, that's about the length of a human limb. A kilogram, well, that's a nice amount of matter you can hold in your hands. And my hands are about a liter in shape. But these are totally random things depending on us being a particular kind of creature on a particular planet. They're not universal. So you want to try to find some units that are based on the laws of nature. And if you plug in the fundamental constants of physics, you end up with the Planck units. They are in some sense natural length scales of the universe. And they are a combination of electromagnetism, gravity, and Planck's constant, etc. And the cool thing about them is, of course, they describe, in some sense, natural length scale for physics. Except that the natural length scale of physics is, of course, also quantum gravity, because we mixed kind of gravity and quantum mechanics. So the Planck mass, that's actually fairly large. It's about 10 to the minus 5 kilograms, or it's a dust grain. But the Planck length, that's much smaller than a proton. The Planck time, well, that's about the time it takes for light to cross the Planck length. So we're talking about a very tiny scale here. And quite often people then say, yeah, that's the smallest possible length of the universe. At this point, everybody starts imagining that's the kind of grid size of the pixels of the universe if it's running a computer. Or if you want to sound more sophisticated, you imagine that maybe space-time is made out of little triangles or tetrahedra as some kind of graph. So the length of the links here are Planck length. And while certainly there are physical theories that are like that, actually, we don't know. The theory about the Planck scale doesn't tell you anything about what's going on there, just that at this length scale, you can't avoid getting quantum gravity effects. And this is problematic because we don't understand quantum gravity at all. Quantum mechanics is very well behaved. It's a beautifully simple mathematical theory. It's even in some sense natural, which is a really weird thing to say because it's so extremely odd compared to our everyday life. And gravity and general relativity, you can get used to it. It's a beautiful theory, but they don't fit together at all very well. You can certainly take curved space-time and try to solve the wave equation on it, and you can even get sensible answers that way. The problem is, if I want to calculate how an electron is moving through space-time, the electron is of course also going to cause a back reaction of space-time. It has a small mass. It's going to curve space and time. The problem is I can't just take a curvature based on its wave function. That's not well defined in this case. I need to, in some sense, model how it could be in any place at all, maybe weighted by the wave function. But now I have a different space-time. Suddenly I need to redo the calculation. And making this consistent doesn't seem to work very well. People have certainly done approximations that sometimes produce reasonable answers, but it doesn't work out very well. There are some rather profound incompatibilities between the theories, which is on one hand very cool, on the other hand super annoying because we would really like to know what happens if you have a piece of space-time down at that size. It seems like we should expect that virtual particles or things like that move around and cause a little wobbliness, but maybe that's a very serious wobbliness that causes microscopic black holes and wormholes and more complicated things to pop up, but we don't know how to handle that. So in the end, this is a very active field of research, and it might be that we're all going about it in totally the wrong way. So the next Einstein is just going to say, look, let's ignore all those fields and tensors and stuff like that, and just think in terms of, let's say, logical gates or something completely different.
Yeah. Yeah, one of the reasons I like physics so much, well, is because of science fiction like Star Trek, Babylon 5, not against various different genres. And I'm just thinking to myself, the universe is a big and strange place, and it's just interesting to learn all the different things about it, like black holes and stars and all that. We've come a long way, but there are still other mysteries. And
Mm.
does that bug you that there's still so much more that we haven't learned yet?
No, that's kind of good news. Just imagine being in a future super civilization, and there is the latest scientific conference, and we have been gathering all the data, and yeah, we haven't seen anything really new for the past billion years. We have actually scouted out all the accessible universe. All our little robot probes have gone off, and we have a complete catalog of all the stars, planet, asteroids, and dust grains. And yeah, they're all belonging to the standard types. And yeah, there was a slightly weirdly shaped asteroid over here. I'm showing a slide and everybody laughs because it's slightly funny. But that's not a very hopeful ending of physics, that we kind of just cataloged everything. So Richard Feynman, in one of his essays, he pointed out that he thinks that physics can't go on forever, because eventually either we end up with this state, we have described everything perfectly well, and there is nothing really new and surprising, or it just keeps on going. Below quantum mechanics, there is quantum gravity, and below quantum gravity, there is something more. And he points out that if you keep on doing this 1,000 times, eventually you probably get fed up too. It's in some sense meaningless if it just keeps on going. Maybe some mathematicians are happy. But there is another reason to be hopeful too. Even in systems that we in some sense understand really well, really weird things happen. So over the past 1 or 2 weeks, I've been kind of obsessing about what kind of systems could make computers. And it's very funny to read up the literature, because it turns out that you can make almost anything act as a computer. So the classical thing is, of course, to have computers running on electronics, but it doesn't have to be transistors. You can use relays or vacuum tubes, but you can replace the electrical currents with fluid flowing through tubes and interacting in little fluid gates. That works just as well. Indeed, it has been used in a few applications, but electronics won out. And it turns out that you can make even more amazing computers. You can use Magic the Gathering cards to construct Turing machines. You can construct Turing machines in Minecraft. In fact, a lot of computer games allow you to make systems that can perform general purpose computing. And you can take tubes and let certain species of crabs walk through them, and you can make logic gates out of that. And a lot of computer software protocols can accidentally act as computers. It turns out that liquids might be able to act as computers on their own. There is an interesting mathematical project by Terence Tao about proving this instability of Navier-Stokes equation, which kind of hinges on him constructing something a bit like a computer that reproduces itself on a smaller and smaller scale, faster and faster. If that system could work in the actual Navier-Stokes equations, which are slightly idealized compared to an actual liquid, which obviously has atoms and molecules that stop this at some point, then he can show that, okay, this liquid can blow up if I give it the right initial conditions. I spent the weekend working on trying to make logic gates for little eddies bouncing off each other, and I think I almost succeeded. I still have some problems to work out. So the cool thing here, and getting back to your actual question, is that this is what normal matter does. Now think about the weird matter we find in neutron stars. Could you make computers out of that? The strong nuclear force is probably Turing complete, but it's a bit unclear whether you can do error correction. Think about plasma clouds in interstellar or intergalactic space. Maybe you could make computers out of that. And this is just computers. There's a lot of other fun and non-trivial things you can imagine them being. For example, life. So it seems like even the forms of matter we think we have a good handle on, like liquids and solids, enable really open-ended complexity. And this is where I'm rather happy that I think science in some sense is never going to stop. It might very well be that we end up with a theory of everything that actually describes what's going on the smaller scales. But that isn't a theory of what can and cannot happen in the actual world, because I can build a really crazy contraption exploiting known physics that does something nobody has ever conceived. Indeed, it's not terribly hard to write a computer program, which is essentially a configuration of matter and energy running on a silicon chip that does something that nobody has ever thought about. Indeed, most computer programs that are possible to write has never ever been written because we are too long, and we could just randomly generate them very easily and get something that has never ever existed in the history of the universe. So it seems like there are some parts of physics that are very open-ended that can do really weird and interesting things. But then again, most of the stuff we get in the textbooks are the general stuff, the stuff that applies to a lot of systems, rather than the really, really peculiar physics of computers and living beings and Dyson spheres and starships.
Yeah, you're right. You're right. Because it would be kind of boring if we just knew everything like
Yeah,
overnight.
and there is a problem here in knowing everything, because our brains are finite physical systems. I got 1.4 liters of neural matter. Sometimes it thinks a slightly rational thought or understands the world a little bit, but it's way smaller than just the furniture in this room. And even though the furniture is not doing terribly much, there is still a lot of complexity going on the macro micro scale over there. Now, if I look out of the window at the blizzard outside, whoa, there is so much more. And it's pretty clear that I can't handle that just with my brain. I can make a nice general explanation of how blizzards work. I can maybe do a computer simulation. Um, so I can certainly do a lot of things. But my brain is pretty limited. My computer is pretty limited. I can, of course, ask more brains with help. We can string together bigger computers, but the universe is always bigger. There is always potential for stuff that is way weirder. And usually you can make really weird effects even by very small amounts of stuff. The complexity you get even in a tiny handful of people or a tiny piece of software is actually quite astonishingly open-ended already that. So I don't think we have any reason to be bored.
Yeah. So those are all my questions. I like the interview again. What did
Yeah,
you think of it?
which one?
This one. What did you think of this interview versus the
Oh,
last one,
I
if you
really
remember?
liked it. It's interesting to get into the literally the heart of matter. I think a lot of people have gotten this weird idea that matter is boring. We talk about mere matter, and then we say energy, spirit, information. But actually, just the ceramics of this mug, just those pigments forming a picture, that's already a lot of very weird physics going on. There is a whole bunch of atoms organized into this weird amorphous matrix that provides a lot of interesting properties. When I was tapping it, you got a slightly high-pitched tone because the speed of sound is really high, which is kind of weird because you would expect in a messy amorphous substance it would actually be slowed down by the discrepancy. Interactions of light between that pigment in my mug and what we see, that's already a lot of complicated quantum mechanics. And that's just a mug I happen to have my coffee in. Around us, there are many wonderful little mysteries. And uh, it's kind of astonishing that it took us so long to discover just how much it was going on. On another level, okay, now we started, but there's so much more we get to see. And then, of course, we start adding information and energy and the action to it, and things get even better.
Yeah. Yeah. Endless knowledge out there.
Yeah, yeah. And it's an interesting thing because knowledge also requires matter. That's the other side of a coin. A lot of people who go on about mere matter being boring think that, oh, yes, knowledge, that's the important thing. And they have some Platonic idea that ideas of a true thing. And then we have these crap imitations in the form of material world. And I think they got it exactly the wrong way. Our ideas, they're math, they're patterns of neural firings. Some of these patterns get replicated when you listen to me. Some of them just get mutated into entirely different patterns. And matter is playing an important role here. There is nothing like mere matter.
Wow. I could talk to you for hours more, but I gotta go help
Yeah,
my family out.
yeah.
But
We have to just do it more. Next time we might talk about energy or some other weird things. There is
yeah,
so much to discover.
yeah. All right. Thank you for your time. Okay.
Take care. Have fun. Cheers. Bye
You
bye.
too.